AFCEA, Hawaii Education Foundation. It's a 501c3 organization that works with the community to collect sponsored dollars to give scholarships to the local high school kids. Since AF's creation, we have raised over $2 million for scholarships and put a lot of local kids through school. You folks being here, and being AFCEA members, help generate the funds that we need to send more kids to school. Okay? These CEO courses, what we're trying to do is hold these courses at AFCEA shows around the Pacific Rim, so Tokyo TechNet, Korea TechNet, to help the soldiers in the DoD community get the CEU credits that they need to maintain certifications and make the next rank or maybe get the next job. So if these courses are valuable, all we ask is that you become an AFCEA member because it's one of our sources of the revenue stream that allows us to continue to teach these courses. Okay? So today, we're going to be talking about optical networking. And before we get into that, I wanted to ask who the Dodgers fans are in the room and who the Astro fans are in the room. None? Oh, okay.
Stros.
I'm from Chicago, so you know where I stand. I want to ask one trivia question before we get started. Years ago, this hotel used to have a unique bird that was here that was on display. And they're no longer here. Yes, sir.
I thought you were going to ask me if I was raising my hand.
Yeah.
Penguin.
Penguins. You guys knew that. This was the only place in Hawaii where you can come and see penguins. And when my kids were little, we used to take them down and look at all the penguins. Okay. So with that said, we'll go ahead and get started. Some of the administrative stuff, as you know, this is a course for CEU credit. And the way CompTIA runs the course, or asks us to run the course, is that the doors are locked. There's going to be no new folks coming in once the course starts. If you leave, we cannot let you back in. So if you have to go to the boys' room or the girls' room, that would be a good time to go. Maybe some speakers and whatnot. The class is scheduled to run 90 minutes. I think the presentation itself will run about 60 minutes with some Q&A, maybe an hour and a half or so, but probably won't go the full 90 minutes. So I can talk a little bit longer if anybody needs to go. The bathrooms are right across the hall. Okay, very good. So with all the administrative stuff out of the way, let me go ahead and introduce the speakers for today. Okay, so the title of the course again is Optical Networking, and our speakers are Jim Hutchins and Brian Thompson. Jim has 20 years of U.S. Navy and intelligence experience as an analyst and cryptologist with multiple deployments around the world. He has over, Jim has over 12 years as a trainer at various training commands. 17 years at Sienna Corporation in tech support, deployment, consultant, and training roles. Currently, he's in a training role teaching Sienna networking products and technology classes and certifications. Brian Thompson. Brian is a senior architect engineer specializing in layer 2 packet optical transport. Brian has 20 plus years within the industry and was brought into Sienna in 2008 as a subject matter expert to work with Sienna's federal government, DoD, and special programs group. He deals with the transformation of optical transport networks and Ethernet. Brian's position serves as a technological overlay to Sienna's government solutions, and he is focused on the development, sale, and execution of all packet-enabled endeavors. Okay, with that said, I'm going to go ahead and turn it over to these guys, unless you have some questions for me. I'll be sitting in the back of the room until the class is over. When the class is over, if you are a AFCEA member, we will scan your badge, and that will be sent in to CompTIA, and you will get credit. If you are a non-AFCEA member, do you have anybody that's a non-AFCEA member? Make sure we'll scan your badge. What we're going to have to do is provide us with your name and email address on a sign-up sheet before you leave the room. We will send you a digital copy of a completion certificate for this course. You have to submit that into your education account at CompTIA. And if you want to become an AFCEA member, then every CE course that you take will become automatically taken care of. Okay? Any questions? Yes?
You only said the CompTIA gives some access, so I need somebody for access.
I think that works as well. Mary,
Yes, we'll take your information down and then we'll make sure it gets to the proper organization.
And I forgot to introduce the other volunteers. We have David in the back. We have another gentleman named Eric, who man the doors to help you folks egress if you need to. Then we have Mary Smith, who's my partner in crime with AF, helping teach the courses. Okay? All right, no questions? Wonderful. Thank you all for coming.
Thank you. So, morning. As he said, my name's Jim Hutchins. I've been at Sienna forever. I have 119 slides to get through in an hour and a half. So I'm going to have to run through a lot of this. I usually have an intro slide, goes over everything. But I'll say if you have questions for Brian or I later, our booth's right on the other side of the wall here. Please come talk to us. So this courseware is non-product agnostic. This is about exactly optical networking. So it is an introduction to optical communications, and we talk about lasers, we talk about photodiodes, and all the things that make optical communications possible. So we'll talk about some of the things that led to development, transport networks, roles, deployment types, related protocols that are supported by optical networks. So by definition, optical communications is transmission of information of light over a given distance. The light being defined by its transmission medium. And in this case, we're talking about fiber. That fiber could either be multi-mode fiber or single-mode fiber, which is kind of defining the distances it's going to travel and the amount of bandwidth that it's going to support. It's propagated down that light source. So I am going to make an assumption that you know a little bit about radio theory. Because light is still it's still electromagnetic energy. So it's still going to travel the same way a radio wave does, or an X-ray wave does, or any other type of wave. And it's collected and interpreted by a receiver. In the case of light, that receiver is a photodiode, either positive intrinsic negative or an avalanche. And one of the things it has to account for are properties of light. It's a wave, so it still has to account for the same things as any other electromagnetic wave does as it travels through the fiber. But there are some unique things that we'll discuss later that do impact light specifically. So, as I said, a lot of things that were led to the development, the transmission medium, Dr. Charles Cal and the papers he published in 1966 saying we could transmit light down a piece of glass. Low sensitive photodiodes, and one thing that's starting to occur today that's being borrowed from the satellite industry are advanced modulation techniques, pushing more data down the pipe. So today, pushing down 200 gig, 400 gig, 500 gig, and eventually probably a terabit, and actually it's already been tested, a terabit worth of data down a single fiber on one wavelength. So today it's already possible having multiple terabits worth of data that's being transmitted down the fiber. So over satellite, copper, and most of our other communication methodologies we've used in the past, light can travel further without having to go regeneration. It just has to be amplified, so it stays in a optical methodology. So it can travel further. It's not uncommon today to see light traveling 10,000 plus kilometers with just amplification. Capacity. We don't know how much you can push down a fiber. Facebook and Microsoft just lit up a fiber from Norfolk to Balboa, Spain. The capacity on the fiber, they're advertising it at 160 terabits worth of capacity on that fiber. More flexibility. We don't care what you're transmitting. It can be Ethernet, it can be anything. Light doesn't care. In the overall scheme of things, it's cheaper. You can push more bandwidth at less cost. And there are some inherent security features that are identified. It's much more difficult to tap a fiber. Microwave, just stick an antenna up in the middle. Satellite, be in the footprint. So it is more difficult to tap a fiber. It's not impossible, but it is more difficult. So I work for Sienna. We focus primarily on transport networks. So the backbone of most networks are high capacity, large bandwidth. But a lot of LANs are also very much dependent upon light now as well. So you're starting to see in the access and in the edge, total optical networks as well. But optical networks are purpose-built for provider to provider. That is, who is providing your services. Commands like DISA, they are a provider. Or provider to enterprise, enterprise to enterprise. Those deployments, tactical deployments in the field, making use of light to communicate and push high bandwidth to your users. So typically transport networks are going to need more bandwidth, more reliability, and standardized manageability to support data center applications, the cloud, whatever that is. Everybody has a different definition today. As well as metro networks, wide area networks, submarine networks. I give you a website, submarinecablemap.com. Every commercial cable that's buried across the ocean up through 2020 is going to be on the website. As well as most of them, you got links so you can get the capacity of each fiber. So it's to transport voice, video, and data across large geographical areas. Triple play was the commercial word we always heard. Today it's just ones and zeros. It doesn't matter what it is. So to support both terrestrial and submarine networks. As I said, a majority of pretty much all of your submarine networks are all fiber today. And being able to support a variety of different physical topologies. Legacy optical protocols were very dependent upon ring-type topologies, whereas modern networks are moving more to physical mesh topologies to take advantage of new management systems and control planes and intelligent networks. So notice there's one missing here, Ethernet. But Ethernet, as well as SONET and SDH, which were legacy protocols for optics. Our newest protocol, which is defining where optical networks are going, is OTN, or Optical Transport Network. It was a protocol that was developed by the ITU and the Standards Committee to manage these newer optical networks, to manage newer management systems and provide management, to manage multiple wavelengths. SONET and SDH could only manage a single wavelength.
So, I'm sorry,
No.
why'd you leave Ethernet out of that?
Because I'm going to talk about it tomorrow.
Okay.
I don't want to steal all of my thunder.
Okay.
Yeah. So there are a number of protocols that are out there to support security and different techniques that are used, both hardware-based and software-based, as well as interfaces, access level. So there are a number of different methodologies that are now in use to provide security for these networks. As I said, whether it's be through hardware-based or software applications and techniques, or directly through the interfaces. So that's kind of an introduction to where we're going to go. So I'm going to talk about light, then the three things that are required to move light down from point A to point B, and then some of the impairments of light. So we'll talk about, as I said, get the math out of the way first. So first of all, we'll talk about and we'll define what light is. As I said, it's another form of electromagnetic energy, expressed as either a frequency or a wavelength. Now, as a vendor, we like to use a thing called a channel, which we think is kind of synonymous with a frequency or a wavelength. It is kind of. A frequency and wavelength are always the same. They're math. A channel is not. So my channel 1 might be different than your channel 1. It depends on where we wanted to start on the ITU grid. But frequency and wavelength are always fixed, and it is an inverse relationship between frequency and wavelength in relationship to the speed of light, and it is the speed of light as measured in a vacuum. Remember, light doesn't travel in a vacuum, which is one of the things we have to kind of consider when we talk about things that are going to impair light as it travels through a fiber. So as I said, it's another form of electromagnetic energy, expressed as either a wavelength or as a frequency. Communications itself is occurring near to the visible range. So we're talking about the optical spectrum as the ultraviolet, visible light, and the infrared ranges. Most communications today do occur in the infrared range. Remember, we're just a small portion of that overall spectrum because it does include as well things like gamma rays, X-rays. With measurement of frequency typically in most of our communication systems defined in nanometers. The frequency is defined in terahertz. For communications, the ITU has established 6 transmission windows that are for use within the communication spectrum. So the O, E, S, C, L, and U bands, the O is the original band, was typically for one of the first bands that was used for single mode fiber applications. Light transmitted at 1310 nanometers. The E band, the extended band, the subband. C is the conventional band. This is where most of our communications occurs today. 1550 nanometers. Then the L and the U bands. One that's not on here in the enterprise space, in the access space, 850 nanometers, because it's down closer to visible light. So light does have both it's very unique, and it has properties of both a wave and a particle. So as a wave, it consists of electrical and magnetic fields that are oriented at 90 degrees to each other as it travels through a fiber. It's expressed as a frequency or a wavelength, or by vendors as a channel. Whereas a particle, it's defined as a photon. For those of you that are Star Trek fans, it's defined as a torpedo. With measurement typically defined or measured in decibels. So light is measured or expressed as an optical power level as a decibel. It expresses a ratio between 2 values, and it's logarithmic rather than linear. So it's typically referenced to milliwatts. So 0 dBm would equal to 1 milliwatt. And any increase in power, every 3 dBm of increase in power is a 50% increase. So a 3 dBm loss is a 50% decrease in power. And it is transmitted through an optical fiber. It's made of pure silica glass. In the US, probably the largest manufacturer and the one that everybody's always heard of is Corning. But there are other manufacturers. Alcatel, I think, still manufactures. There's a company called Draca. There's Teralight, so there's several others. And the light itself does consist of 3 components. A core, nearly pure silicon dioxide. And it's typically doped with something like germanium in order to provide it with unique properties so that it can maintain the light within the core. The cladding, which is also nearly pure silicon dioxide to surround the core, to confine the light to the core. Then a buffer or a coating to protect it and make it easy for you to handle it. So we're dependent upon that light to propagate through the fiber. The ability to travel over that and ensure that it is reflected and refracted within the core of the fiber. So it's defined to stay within the fiber within total internal reflection, which is defined as refraction. It bends at that juncture to reflect into the optical core and refract. Snell's law, there's plenty of math if you want to go look at the math to define refraction. And refractive indexes, the ratio of the velocity to the speed of the fiber as versus the speed of light in a vacuum is Snell's law. But light is totally dependent upon reflection and refraction to ensure that it travels through the fiber. We have the same with radio. HF, the Earth's surface and the ionosphere. We just have a bigger medium. So reflection is the change in direction of that light ray, where the light bounces back into the original material. So between the core and the cladding of the, and as I said, Snell's law is the ratio of the sines of the two. So defining how that light's going to travel within the fiber. This is all he wanted me to talk about all day. Because he said if his customers understand all of this, his life is 200% easier. Manufacturers define a cone of acceptance for light as it enters into the core to ensure that it is going to enter at the right angle to stay within the fiber so that you're getting maximum distance and maximum bandwidth for that light as it travels through the fiber. It's specified by the numerical aperture, which is based upon the refractive index of the core and cladding material of the fiber itself. So Corning, Terralite, Draca, they all have different materials that they use when they manufacture their fiber. Different dopants that they use to ensure that they're going to get the maximum distance, maximum bandwidth out of that fiber. The angle of incidence and total internal refraction, or total internal reflection, is, once again, it's defining how that light's going to travel through the fiber. And to ensure, once again, that you're getting maximum distance, maximum bandwidth of that data as it's traveling through the fiber. And because light is a little bit different than radio, there are things that can impact how it travels through the fiber based upon total internal reflection, refractive indexes. So one of those things is dispersion. It distorts the results of or it's the broadening of the wavelength as it travels through the fiber. So dispersion is exactly that. It's dispersing. The further it goes, the more it spreads. Because remember, it's not traveling in a vacuum now. And in today's networks, multiple wavelengths are traveling on every fiber. So dense wave division multiplexing. So dispersion, those wavelengths are going to eventually overlap each other. So you can no longer distinguish one wavelength from another wavelength. So it is an impairment that it limits how far you can travel. The higher the bandwidth, the higher the wavelength, the more bandwidth the wavelength takes up, the more susceptible the system will be to dispersion. So there are intermodal is occurring in single mode fiber, which is chromatic and polarization mode dispersion. Intermodal occurs in multi-mode fiber because the light can take multiple paths through the fiber. So chromatic dispersion is the spreading of the wavelengths. Polarization mode dispersion is when the horizontal and the vertical or the electrical and magnetic fields are not in sync. So one's traveling faster than the other. Now, both of these can be compensated for to a degree. I hope I'm getting too far away. There we go. So chromatic dispersion is the more common of the two. It typically occurs that anything is being transmitted at 10 gigabits or higher. And as I said, it's the spreading of the light wave as it travels through the fiber. The further it travels, the more it's going to spread. And it consists of both material and waveguide dispersion. Material, different wavelengths traveling at different speeds within the fiber. Those wavelengths will then overlap as they're traveling through the fiber. And the further it travels, the more it's going to disperse. Whereas waveguide dispersion, as light passes within the fiber, some of that light may pass, and in all cases it will pass, some light goes through the core, as well as some light is going to pass through the cladding. The majority of the light is, however, in the core. And the light that's traveling through the cladding is defined by the effective area of the fiber. So Corning and other manufacturers have come up with different methodologies in which to change the effective area of fiber, so they manufacture it for specific applications. So although the core itself is round, the effective area will be triangular to make it maximized for things like dense wave division multiplexing. So they try to attempt to control waveguide or material dispersion. Whereas polarization mode dispersion, polarization modes traveling at different speeds. So the vertical versus the horizontal, so that one is traveling at a slightly faster speed than the other. It typically is not as big of an issue at 10 gig. It becomes more of an issue anything that's transmitted at 40 gig and higher. And as I said, they can both be compensated for. Today, it's usually done electronically. So actually intelligent transmitters and receivers that communicate between each other across the fiber link to allow the fiber itself to become a compensator for cleaning up the signal. It's usually done by introducing chirp on the laser or usually chirp. That way you're sending a dirty signal into the fiber will clean it up as it goes to the far end. And that's done in near real time.
Kind of like our analog repeaters.
Exactly. This is not new.
Different medium, same technology.
Exactly. Exactly. Very similar. Nothing, like I say, nothing new here. If you could do FDM, you could do DWDM. Yeah. So with higher rates as well, other nonlinear effects, stimulated beryllium and stimulated Raman scattering. These are kind of unique to light. They're both acoustical effects. Beryllium scattering is caused by vibrations in the fiber, whereas Raman scattering is actually an optical energy transfer. Longer wavelengths will absorb the power of shorter wavelengths when they're separated by about 100 nanometers.
So earthquake can cause beryllium.
Yes, and actually you can,
Or jackhammer.
yeah. The Israelis are actually using beryllium scattering in their fiber networks. They're using it to discover tunnel digging.
Pretty smart.
Yeah. So if they're detecting beryllium scattering on their networks, they're using it to detect tunnels.
I can use a OCDR to figure out how far that
Yep.
beryllium scatter is.
Yep.
That kind of thing.
Yeah, you can, so they're impairments, but you can use them to your advantage. So Raman scattering is often used as an amplification technique. You send a lower wavelength and the higher wavelengths will absorb the power. Self-phase, cross-phase modulation is based on the refractive index of the fiber. And wavelengths can modulate themselves or modulate other wavelengths. As well as four-wave mixing. In the radio world, we call this harmonics. It's an optical harmonic. Whereas the wavelengths, the more tightly spaced they are, they can generate ghost channels, or they can generate harmonics. So now let's talk about those things that are required to get A to B. The transmitter, the receiver, the medium, and a way to modulate the signal. And I didn't say this up front, but most of you have taken the cue. If you have a question, don't hesitate to stop me. So modulation. We've modulated in radio forever. With light, we could do Morse code. You just put a paper in front of the light, it's digital. I was a Morse code op. That tells you how old I am. The first binary system, on for a 0 was a da, and a 1 was a dit. So there are a variety of techniques that can be used to put data onto a transmission medium, or onto a carrier wave, or a modulating wave, and then extracting it at the other end. The transmitter is either a laser or a light-emitting diode that processes the signal for transmission over the link. So it's a laser or an LED with additional components. The receiver is a photodiode at the other end and the components to convert it from optical back to electrical. So we're doing a digital to analog conversion and then an analog to digital conversion. And in the medium, we talked about fiber. So modulation, there are a variety of ways in which you can modulate the signal. But modulation itself, we all know that's a process of how you change the characteristic of the wave to impose data onto it. In the case of light, you can turn it off and on. You can change the phase. You can do a phase shift. Same things we did in radio. In light, instead of amplitude modulation, it's intensity modulation. We're just modifying the intensity of the light. We're turning it off. So that wave has to be modulated either directly or indirectly. Directly is typically used for anything that's 10 gig and below, with indirect modulation being done to vary the output for 40 gig and higher. Indirect is more expensive because it requires more components. It requires more materials. It's more sophistication.
Can it be done on the existing infrastructure? 40?
Yes. So 40 gig, 100 gig, 200 gig, 500 gig are all, yes, they're all being manufactured to take advantage of the existing infrastructure that's in place. We do it constantly. You know, one of the demos that we'll do a lot of times is, you know, you'll have a 10 gig channel and a 200 gig channel on both sides of it, and it's taking up the same amount of spectral width, same amount of space. Because that's the advantage, maintain your infrastructure, particularly in the submarine world. It's not easy to go yank a fiber up off the bottom of the ocean. So as I said, you can modify the amplitude, modify the intensity, the phase, or the polarization. And in many cases, because with polarization you have access to both the horizontal and the vertical, you can do dual polarization. Therefore, you can manipulate the signal and you have access to both phase and amplitude. So you can process more data and you can send more data through the fiber. Because everything is defined as a symbol. A symbol is conveying information. And a symbol can be a single bit or it can be multiple bits, depending on the modulation technique that is used. So as I said, it could be something as simple as on and off. It could be a phase shift. So you do radio a lot, right?
I was a signal for 2 million.
Okay, so yeah. So this is, it's nothing new. Binary phase shift keying, quadrature phase shift keying, dual polarization quadrature phase shift keying. You're just modulating the phase of the carrier to encode data bits. You know, in SONET, STH, and single channel systems, it was always binary. 0 for a 1, or 0 was off, 1 was on. Quadrature, you're transmitting 4 different discrete phase states and carrying 2 bits per symbol. Yeah. You want the mic? You want the mic?
No. I'm a senior network engineer. I don't do transport.
Oh, okay.
So I'm trying to get more smart on the
Yeah.
transport.
Come talk to me later. Yeah. So the transmitters, your lasers themselves. Transport defines or is more dependent upon lasers because it's a more intense light signal. It's a concentrated beam of light. It's synchronized in phase and time, so it's considered coherent light. So transmitting over long distances and high bandwidth. But it's still, in most cases, it's based upon lights being produced by an LED. And LEDs are incoherent light because the light's produced by an LED is transmitted in arbitrary directions. So it's not synchronized. It's emitted in a cone shape, so less bandwidth and shorter distances. And we use them everywhere today.
LEDs would be what you'd use on your land side.
Yes, usually you use them on the land side. And we see LEDs everywhere today. It's not just in communications, they use them everywhere. Everything on my motorcycle is an LED.
Yeah.
The headlight, the turn signals, everything, which is going to cost a fortune when one of them breaks. So for lasers, there are a variety of different lasers. These are three of the more common ones. Distributed feedback lasers, Fabry-Perot lasers, are edge-emitting lasers. In other words, the light they produce is emitted through the side of the lasing cavity, whereas the vertical cavity surface-emitting laser is exactly that. The light comes out the top. There is a difference between the two. So the DFB, distributed feedback, and the Fabry-Perot have to be tested individually, and they can't be tested until after you manufacture them. So they cost more. The Fabry-Perot, based on the Fabry-Perot interferometer. And it does a very wide spectrum laser, whereas the distributed feedback laser is a very narrow spectral laser. So each one are used for different applications. The V-cell is actually, it's optimized for use with multimode fiber. So it's more a landside type application. But the advantage of it, because it's a surface emitter, you can test it during manufacturing, and you can test in batch. So it saves money. And things that will impact that laser itself and how it functions in your network. Chirp. Directly modulating it causes the wavelength to shift. And remember, chirp is one of the things that's introduced because it does have an interaction with chromatic dispersion. Because it is a broadening of the wavelength, chirp causes it to broaden. So introducing chirp can actually be used for electronic dispersion compensation. Back reflection creates noise, and that's any light when it's reflected off of a mirror and re-enters into the lasing cavity. And then temperature, being able to maintain a constant temperature and be able to stay at room temperature. So using things like Peltier coolers, thermal electric blankets, thermal electric coolers, to ensure that you're being able to maintain a constant temperature because they're electronic devices, they generate heat. And in some cases, the high bandwidth, they generate a lot of heat. Whereas your receivers are photodiodes. So we'll talk about a couple of different types of photodiodes that you can use. They're responsible for converting the light back. So they kind of do the exact opposite of what your laser did. Now there are two different methods that can be used. Direct detection, typically for 40 gig and lower, and coherent detection for higher rates. But there are some that use coherent for 40 gig as well. So direct detection, you're a photodiode that's converting the incoming signal directly to electrical current. So as I said, it's typically used 10 gig and below. Coherent, because it's used with your more advanced modulation techniques. So you're looking at 40 and 100 gig plus DWDM line rates. So you can't convert back that fast. So photodiodes are semiconductors. They're the receiver for any of your optical traffic. With the two main types, the positive intrinsic negative photodiode or an avalanche photodiode. So a positive intrinsic pin, it's defined by the manufacturing technique. It's a positive semiconductor material, a negative semiconductor material, and an intrinsic material between the two. Pretty much. The difference between these two, the avalanche is more sensitive, so it can detect light at lower levels. It also does provide, the industry defines it as an amplification. It is kind of. Pins, every photon that they detect, they create one electron. Whereas an avalanche, for every photon that is detected, it creates multiple electrons. So it's defined as an amplification. I don't really consider it that, but the industry does.
Avalanche starts with one that goes to many.
Yeah.
I guess.
Whereas coherent detectors are used for your more advanced modulation techniques. And it's actually multiple photodiodes synchronized to a local oscillator, and it gives you the advantage of you have access to both phase and amplitude.
Sounds like it's a relatively complicated detection method,
It is.
because you have to eliminate duplicates and
Yes.
transmits.
So coherent, as I said, they're usually used with your dual polarization schemes for 40 gig, 100 gig, 200 gig, 800 gig, and terabit. Because those applications, they cannot be detected through direct detection. In the medium, we talked about fiber. So we'll talk briefly a little bit about the physical constructs and the two different types of fiber you can deploy in the network, either single mode or multi-mode, and then how it propagates through. So as I said, it's a low-loss transmission medium consisting of a core, a cladding, and a buffer. The core, nearly pure silicon dioxide for single-mode fiber, it's 8 to 10 microns.
And you said it was a galvanium or
It's
coating on the inside of it?
is typically they use germanium, but I've seen arsenic. In the case of dense weight division multiplexing, erbium, thorium. So there are different materials or different elements that can be used depending on what properties you want to get.
It's used to increase the reflection capability of the internal.
Well, and in the case of erbium, it's actually used to generate light as an amplifier.
Every time it hits, it adds to it.
Yeah. But erbium only reacts with certain wavelengths.
Right.
So there's I assume a lot of trial and error. So it's manufactured either tight buffered or loose tube for a variety of different applications. And you can get simplex fiber, duplex for distribution and breaking out at patch panels, armored cable for outdoor deployments, several sheets of Kevlar, which still does not make it backhoe proof. Same thing, submarine cable, multiple stainless steel jackets, Kevlar, which does not make it anchor proof. And in many cases, close to shore, it's still even buried and still doesn't make it anchor proof. Yeah. So single mode is typically used for most transport applications, whereas multi-mode is used for a lot of your shorter distances, because multi-mode is shorter distances and not as much bandwidth. So like anything else, the further the signal travels, the more it's going to lose power, the more it's going to attenuate. So loss is going to cause anytime that signal is interrupted. The total loss, all the reflective light, the optical return loss itself. And it's measured in decibels. So a lot of things that can contribute to that, anytime there's an intersection. Or other anomalies like absorption. Like everything else is going to absorb the fiber itself is going to absorb part of it, convert it to heat. It is wavelength dependent. Scattering, bending losses, Fresnel reflection splices, all of these will lead to attenuation. Scattering is Rayleigh scattering. Bending losses, micro bends and macro bends. Micro you can't see, macro you can. And in many cases, micros, it's caused either a manufacturing flaw or in the commercial world, the fiber troughs that they have running throughout the central office, when they terminate a circuit, they don't pull the fiber out. So all the fibers on the bottom get stuff in it. Splicing a fiber, whether it's mechanical or whether it's a fusion splice, and my favorite, there's the last one there, good old dirt.
What's your experience with fusion splicing? Is Is there a significant loss in the internal coding and possible skipping on
No.
the splice?
Fusion is actually better than mechanical.
Because I'm just thinking at that fusion splice point, much like a weld,
Yeah.
you won't have that internal galenium coding. So if you're actually hitting at that weld point with your light, isn't it possible to get a skip effect or
You would have, I would have said yes 5 years ago.
today not so much?
No.
Okay.
These splice units are really, they're even sailor proof.
I wouldn't go that far.
Yeah, they are.
I've worked with it, but I wouldn't go that far.
The splice units today, they are idiot proof. And I used to say that God would always invent a better idiot. I think we give him a challenge finally. Because the only thing they can screw up is they splice the wrong two fibers together. So they can still do that. But other than that, the splice unit itself does everything. You put the two fibers in, it brings them together, it does the splice, it measures it, it does everything. And it's no bigger than her purse.
They even do a tension test on it. It does
Yeah.
everything just to make sure that the weld's good. It even does a dB loss for you where on average you don't accept anything over a 0.03, but you never really get anything unless your cleave's wrong over a 0.02.
Yeah, and that's it. The only thing that's the other thing that your tech can screw up is a cleave when he cuts. And it'll tell you that. So the splice unit itself is smart enough, oh, you got a bad cleave. I'm not going to cut
You
it.
can even see it with the cameras that they have on the
Yeah.
X and Y cameras. So
It won't let us happen because we're on the edge. So it's like end to end.
But yeah, it's amazing what these new units can do. Some of the older units, that was very possible for that to happen, though, yes. So within the last 15 years, the networks have started to transition, mainly because of bandwidth demand. And once again, you ask about the infrastructure, maintain the infrastructure without having to put in, because laying fiber in the ground is expensive. So moving to putting in more wavelengths on the fiber, dense wave division multiplexing. So every vendor, we manufacture hardware to give you as many wavelengths as possible on that fiber. So the DWDM grid is defined by the ITU is literally hundreds. I don't know anybody that uses the entire grid. But I've seen over 200 wavelengths that have been placed onto a single fiber. So different hardware that gets placed in there, client cards, that's facing to your LAN. The network card or the line card, that's generating your dense wave division multiplexing frequency or wavelength that's going to be placed onto the fiber along with everybody else. Then those wavelengths are multiplexed together to be transported across, and then they're also filtered out because a photodiode is not a wavelength filter. It's a light detector. So if you hit it with 1550 nanometer light, 1310 nanometer light, and 850 nanometer light, it's going to try to interpret all of them. So a filter is a way to ensure that the correct wavelength is going to the right pin or the right receiver. So there are a variety of methods that can be used to filter light. They can be fixed filters, so you can cascade them, daisy chain them throughout the network using things like fiber Bragg gratings or arrayed waveguides, or even what's becoming more popular now, colorless solutions, tunable receivers. So Bragg gratings is like an interferometer, but it is a piece of glass. You create grooves on the glass, and the glass will reflect unique wavelengths. And then you use a circulator to ensure it goes to the right location. Arrayed waveguides are higher capacity. They add drop everything. So they actually use heat and phase shift in order to detect unique wavelengths.
Like the waveguides on the dish, right?
Right. And mostly transmitters and receivers today are packaged together in form factor pluggable units. So the industry standard, they're FPs, so small form factor pluggable, 2.5 or 4.25 gig and below. XFP, X is Roman numeral for 10, stands for 10, it's for 10 gig applications. For 100 gig, C. They also use the C for, I didn't want to do an XL, so C is also used for 40. There is also a new, relatively new, an SFP Plus, which is the same size as an SFP, but it does up to 10 gig, so the X is eventually going to stand for extinct. The QSFP is actually a CFP4. So the QSFP28 is the 4th generation of CFP. So there's a CFP1, CFP2, they skipped 3 and went to 4. So the QSFP28, and in all cases, the CFP is just like the XFP to the SFP Plus, smaller. And the whole reason, terminate more ports. Terminate as much as you can on a line card. It creates its own problems though.
So we've gone from using 4 10 gigs to get 40 gig to a single.
140 gig interface. And now think about that. Eliminate 10 gigs and get 100 gig interface. Or eliminate 400 gig interfaces and get one 400 gig interface. A lot of eggs in one basket.
Are there any theoretical limitations to the optical infrastructure as far as bandwidth?
None that I am aware of.
I would think you would get a physical limitation
Yeah.
when you start implementing software.
He might.
on top of it.
Is there a physical limitation you know of yet on the infrastructure?
Physical?
Yeah.
You can only have so many phase shifts you can do, right?
Can't hear you?
You only have so many phase shifts you can do, so I would think it would be a theoretical physical limitation, but then you could augment that with the software before you hit the physical to do something like that. So your theoretical limitation on the overall transport would be maybe limitless.
That or regen.
Yeah.
So the old infrastructure handling, small slow links can be used pretty
Yeah.
much almost indefinitely.
Yeah. And I've seen with these new techniques, I've seen some applications that couldn't run 10 gig that run 200 gig. With the older modulate, they couldn't even run 10 gig. But they were able to process 200 gig. So as part of dense wave division multiplexing as well, able to switch wavelengths rather than take it back to an electrical state so you could send it to a different direction. Wavelength selective switches allow you to redirect wavelengths without having to go back to an electrical state. Because every time you go electrical, it costs you money. You have to have the card, plus it introduces latency, so there's a lot of issues that a WSS allows you to overcome. So you can direct wavelengths or groups of wavelengths to any outbound fiber on any port off of that wavelength selective switch. And the wavelength selective switches they're micro electromechanical systems. So micro electromechanical mirrors that allow you to redirect wavelengths into up to 8 different directions. There are a couple of vendors now that allow you to do up to 20, which introduces its own troubleshooting problems. It's a little more difficult to trace your light, but in addition to that, DWDM, amplifiers. So once again, Sonnet SDH, Brian mentioned regeneration. Amplifiers allow you to extend the reach optically. There are 2 types of amplifiers that can be used. Erbium doped fiber amplifiers, I mentioned erbium a little earlier. It's a rare element, for those of you that care, it's number 68 on the periodic scale. And it has some very unique properties in how that element interacts with 1550 nanometer light if you inject 980 nanometer light or 1480 nanometer light into that erbium doped fiber. It actually causes the erbium ions to become excited and they produce light. And that light is absorbed by 1550 nanometer light. And typically they're deployed in conjunction with each other for the lasers to inject the light, 980 and 1480. Because they each have their own unique properties. 980 gives you less noise. It also produces less power. So it's more for when you're concerned about your signal-noise ratio. Whereas the 1480 is all about power. It's a Tim Allen kind of application.
So the likelihood of these injecting additional noise?
Yes.
The extended length, you may get additional noise on
You'll get additional noise.
Now, is there a filter?
You can use,
on the
yes.
other end to-
So yeah, you can have, so throughout the network, you can deploy filters that will filter out noise. Or your other amplifier is a Raman, using Raman Scattering to provide amplification. And it's usually a counter-propagating signal. So it's actually going out and meeting the incoming wavelength to amplify it out in the fiber. So what they give you for a card to put into is a laser. The amplifier is the fiber.
When do you typically use something like this?
I'm sorry?
When would you typically use something like this? Whatever you, just some examples.
Long-haul transport.
Yeah.
You use it throughout the network
If I wanted to go optical from West Coast to East Coast without having any electrical.
without any electrical whatsoever. And it's very common today to go from New York to Los Angeles or go from Los Angeles to Tokyo,
where I want
and it never goes electrical.
Switch path or a redundant or a path that has resiliency. I just want, literally, I want to go from here to here with no possible interjections. You would need applications to get to that distance.
And these are typically, from a manufacturing perspective, in two types of packages. One costs more than the other. The fixed is cheaper than the variable, because the fixed is exactly that. You get what you get. That's what it was manufactured to provide you for power. That's the amount of power it gives you. The variable uses variable optical attenuators that are software controlled, so you can vary the gain. So you can use it to somewhat control noise, as well as you're controlling the power you're injecting into the fiber.
So you can adjust the power amplification with the variable gain.
Yes. And the variable gain allows you to do things, if you increase the number of bandwidth, the amount of bandwidth you're putting into the fiber, the amplifier itself can adjust to that automatically.
Whereas a fixed may be a fixed throughput.
The fixed, it's all manual to give you more power. So you're typically going to have to interrupt traffic and interrupt service if you want to make any changes to your network. So we'll hit some terms here. The transition from the dinosaur network to plesiochronous or near synchronous to our new, and SONET, SDH, and OTN. SONET and SDH are kind of synonymous, although they are a little bit different. They were,
One's Europe, one's US.
yeah. Well, one's the rest of the world.
That's good.
Yeah, the only people that use this SONET is us. But there's a reason. We had a 5-year head start. So the Europeans took the SONET standard and improved it.
Kind of like T1, E1.
Exactly. So yeah, they took the SONET and they said, we'll improve. They did, and I will be honest, I think it is better with the improvements that they've done. But we had a 5-year head start, so we had too much money invested in infrastructure to change. So they compromised so they could be compatible. Then the newest is OTN, which allows you to manage those dense wave division multiplex networks, which is the majority of your transport networks today. Put as much bandwidth as you can into the fiber.
So if I hear somebody talking about we're putting up an OTN path, that's a DWDM.
That is a DWDM path in all likelihood. Also, requirements for carrier grade and protection schemes, topologies. So some of the terms that you client, your LAN side, your edge, or the access side. That's the signal that's coming in from your other, and client may be your own traffic. So it doesn't necessarily mean that it's going to be an end user's traffic. It all depends on the application. Transport lines, that is the network side. That's your DWDM wavelengths. That's probably an OTN wavelength. OAM is based on FCAP. So OAM, operations, administration, maintenance, that's day-to-day operations of the network. With FCAPs is actually standards, the fault configuration, accounting, performance, security. It's actually a standard that defines OAM. So there are ISO standards and ITU standards that define the way you're supposed to manage your network. Different things that your network has to accomplish to be FCAP's standard. And last but not least, your contract, because that's what it is. Your service level agreement. That's the contract between the provider and whoever they're providing services for. To me, I really believe, because there's service level agreements everywhere today. Because I have service level agreements with my customers that I provide equipment to. And I really believe that SLAs, because I've seen SLAs be as little as a single page. I've also seen SLAs that were volumes. I really believe that they're totally dependent upon the number of lawyers you have on your staff. The more you have, the bigger it's going to be. And somebody has to read that thing. That's a good summer intern job.
That's a good assumption.
Somebody actually going to read it.
All right, just give me my, wait, what do you mean you don't support it?
Yeah. With a variety of different deployment methodologies, international exchange or IXCs, long-haul terrestrial versus long-haul submarine. Long-haul terrestrial, it's on the ground. In the US, that's the network that's going from the East Coast to the West Coast. In Europe, it could be a single carrier that's going across the entire continent. Orange is pretty much everywhere in Europe. T-Mobile's all over the place over there. So even in Europe, a long-haul terrestrial does not mean that it's actually confined to a single country. Then long-haul submarine and all the connectivity coast to coast, continent to continent. Access, metro, and core are typically defined within terrestrial networks. Access, that is typically your local LAN, which is kind of open to interpretation today as well, because there are some pretty large LANs out there today. Metro, those metropolitan type networks, once again, very open to interpretation. The ITUs attempted to try to define what they are, the IEEEs try to define what they are, and their definitions are 180 degrees apart. With core being the core of the network. That's your long haul, that's backbone, high speed, high bulk data transport. Yeah, and all of those are associated with, the local area network is the access, the metro area network with the MAN, the wide area network with the core. But once again, a lot of that, as I said, is very open to interpretation today. And the way that the ITU defines it with the IEEE, their definitions are 180 degrees apart. So in reality, it's a network.
A lot of times using the same technology.
Yes. So we've seen it, within the past 50 years, a huge transition. Sorry, it's a PDF. So PDH introduced in the US in 1965, and the rest of the world picked up a couple of years later. That was in the US the T carrier system. The rest of the world went with the E. With SONET introduced in the United States, it was published in '84, was actually deployed in '85. It was the first standard for optical transmission on the planet, and it was defined as a methodology for the US to communicate with Asia. We didn't want to talk to the Europeans. The Europeans took the SONET standard, took 5 years, they improved it. They introduced synchronous digital hierarchy. And the big difference was SONET was based on the T carrier system. SDH was based on the E carrier system, so they were both designed to transport that PDH traffic. They were designed around voice. Then we had this thing called the internet that kind of happened in the 1990s. Kind of blew our world apart. The networks were designed to transport voice. The internet was definitely not voice. Plus the amount of bandwidth that was being generated, the networks could not handle. So dense wave division multiplexing was the first solution that was introduced to allow more bandwidth to be placed onto the network and not make changes to the infrastructure. But there was no way to manage all those wavelengths. Sonic could manage only one. So any management was always proprietary to whoever manufactured whatever you had. So the International Telecommunications Union introduced OTN, Optical Transport Network. It's a methodology and it's a standard to manage multiple wavelengths. And the networks have continued to grow based on those OTN standards now with next generation optics, advanced modulation techniques to push more data down the pipe. Introduction of 100 gig, 400 gig, a terabit eventually. Then being able to provide semi-intelligence within the network with control planes and management planes so that the network can maintain itself. The network can self-heal if there's a failure. This network can provide end-to-end provisioning. End-to-end provisioning irregardless of the vendor, which is where SDN is going to start to play, software-defined networks, which is our right now the latest iteration. How the network is you're going to be able to provision from New York to Tokyo, a circuit, irregardless of vendor, to get from New York to Tokyo. And the network is going to provide you those resources. With the thought being that even eventually, maybe even the application will just be able to ask for bandwidth and no human intervention. So PDH was our T carrier, the E carrier, and for a little while the J carrier. All based on copper. By today's standards, extremely low bandwidth. Sonnet and SDH was designed to transport that. But DWDM was there to transport Sonnet SDH primarily. Dense wave division multiplexing to allow you to transport multiple wavelengths over the same fiber. Very much like interstate travel.
Traffic and loss.
Yes. Each wavelength has their own lane. Everybody stays in their own lane. There is no road rage. So you increase capacity without having to expand your existing fiber plant. So a fiber that was carrying 10 gig yesterday can now be carrying a terabit, 2 terabits, depending on how many wavelengths you put on it.
So switching over from a SONET to DWDM, pretty much you're just having to change out the equipment.
Just changing the equipment.
The multiplex.
Yeah.
Is it?
And usually you're not even going to do that. You're just going to put a DWDM system behind the Sonnet system if you want to maintain your Sonnet network. And then eventually, you'll eventually pull it out.
So if you're working with Sonnet rings and we're shifting from Sonnet to DWDM, the DWDM form a fourth Sonnet ring, or?
It depends on the vendor at that point in time. Some vendors do support ring topologies. Others are linear, just point to point.
Right.
And you're depending upon the Sonnet ring for your protection mechanisms.
But if you have 3 Sonnet rings and you're adding DWDM, would you?
You could add a fourth ring.
Fourth ring?
You could.
Does that make sense?
Yes.
And it would just be DWDM?
It'd just be a DWDM ring.
DWDM ring, and then put your 3 rings through your DWDM as opposed to having 3 independent Sonnet.
Did I hear, the question was?
So if you have, if your network is Sonnet and you have 3 Sonnet rings, you're shifting over to DWDM, when you shift over to DWDM, would that create a fourth Sonnet ring?
Yeah. It could be. It doesn't have to be.
And probably not best practice then, since no one seems super excited about that.
What's that?
I said probably not best practice then.
No. It's kind of a waste of your resources.
Okay, thank you.
It's a waste of resources. I mean, you could do it, and I'm sure that he would be more than happy to sell it to you, but
Yeah, I actually would probably want to
Ethernet, let the MPLS handle it on the transport side.
Yeah. So yeah, to me, you can do it, but it'd be a waste of your resources
Be fun.
until you had to troubleshoot it. Until you had to troubleshoot it. Yeah. Remember, I used to work in tech support too, so troubleshooting is always at the top of my list. Troubleshooting is always at the top of my list.
Well, that's because it's usually a layer 8 problem, isn't it?
Yeah. Yes. So the different optical protocols is that SONET was the first introduced protocol. It's now considered mature. In other words, legacy. It is based upon time division multiplexing. It was developed in the US by the Exchange Carriers Standards Association for ANSI. It was published in 1984, deployed in 1985. It was designed to transport PDH. So it was designed to transport voice. So everything about it was still dependent upon Nyquist theorem and 8,000 samples per second, and all the data rates and everything else was defined by voice. So everything about it was base 8. It has evolved over time to be able to support things like Ethernet. It's been evolved over time to support video and other applications, but you typically end up wasting bandwidth when you use it as a transport mechanism.
So that's a pin-up method, right? You pin up a certain amount of bandwidth,
Yeah.
period, whether you use it or not.
Yes, SONET is always dedicated bandwidth. Now, ATM was designed with SONET in mind as its transport mechanism. So asynchronous transport mode was designed because ATM didn't have a transport. So it was very parasitic in nature. It had no way to get there. It had to have a ride. So I'm a sailor. So to me, ATM is very much like a Marine. It has to have a ship or it has to have a plane. It needs a ride. It can't get there by itself. So it does have to have a way to get there. But it was designed with SONET in mind as the transport mechanism. So it was designed initially to provide common transport between the US, Canada, and Asia. And the S stands for synchronous. So it is a common clock reference. So it can be either externally, so it has to go to an atomic cesium clock. And it can either be directly to the device, or it can receive that time from an optical link. So it's designed to transport traditional PDH traffic. But the SONET rates were defined around those rates. So in the SONET world, the optical component was an optical carrier or an OC. They're all multiples of 4 to make us compatible with SDH. Because the SONET standard initially was much more flexible. And so the amount of traffic that you can transport, and although the slide goes up to 40 gig for SONET, I don't know anybody that ever deployed it. It was not cost effective. By the time it was introduced, OTN was a much more common transport mechanism by then.
192 is the biggest I think we deployed.
Yeah, 192 is about the largest you're going to see for SONET. Whereas SDH was the rest of the world. It was developed by the CCITT. They were the precursor to the ITU. Their purpose was country to country and global telecommunications. It was designed to be compatible with, but not identical to SONET. It's still synchronous, so it's still dependent upon that common reference clock. So the rates are still multiples of 4 because SDH was based on PDH. Synchronous digital hierarchy was based on plesiochronous digital hierarchy, and everything in plesio was multiples of 4. So we adapted that in the US for the SONET standard to be compatible. And although SDH was designed around the E carrier system and SONET was designed around the T carrier system, they can transport either. So SONET can transport E1s, and SDH can transport T1s. It's not pretty, but it can happen. Whereas OTN is an optical carrier transport technology. It has a wavelength switching capability, so switching wavelengths when deployed with wave division multiplexing. So it's designed to manage DWDM networks with a standardized sub-wavelength switching capability. So if you take the traffic to an electrical state, you can still do electrical switching. So you can still do multiplexing. So you can multiplex lower rate traffic to higher rate traffic, and you can switch at those lower rates. It's based upon a digital wrapper concept, so it is 100% transparent. It does not care what the signal is that it is transporting, as long as it is digital in nature. So about the only thing it can't transport is...
Jim, you have about 8 minutes left
Okay.
for the class.
I knew I was going to run out of time.
All right, sir. Do a good job.
Okay, so about the only thing I know it won't transport is X.25.
I would say who uses that anymore, but
No, there's still a few that use X.25.
especially if you think about mission stuff still out there.
Yeah. So it supports higher data rates, sub-wavelength switching. It also standardizes a forward error correction mechanism. So it does support FEC based on Reed-Solomon. So it allows you to transport traffic even further without having to go to an electrical state. And it standardized its own overhead to manage the network or its own OAM. So kind of comparing the two, you ask about protection. SONET does have more protection by standard than OTN, because SONET does support rings, OTN does not by standard. So that's I was kind of hesitant to say you could do a DWDM ring, because you could, but it's the ring itself, it would be some proprietary mechanism to provide your protection. Because OTN only does 1+1. So some of the things that are required there for carrier grade, and the bad word today is in the one kind of up from the bottom, low latency. Everybody complains about latency today, even though they don't know what it is half the time. So reliability. SONET defined the standard for reliability. 5 nines, 99.999% available. Sub 50 millisecond protection switching. So you get a failure, you get 10 milliseconds to recognize it and 50 to ensure that the network recovers. So you can provide that reliability through redundancy. Calculate your network availability and provide redundancy through network elements, redundant paths, or both. How do you react to that? 1 to 10 milliseconds to determine when there is a fault, 50 to recover your network. Then different protection mechanisms, whether it be client-side protection, network-side protection, or both, and in many cases, in the case of SONET or SDH, typically a ring. Capacity, with DWDM, terabits worth of data traveling down a fiber. And then based upon your fault capacity accounting scheme and security, standardized OAM, as well as management that's provided either in band using the overhead associated with OTN or using an optical supervisory channel that is a dedicated wavelength for management. And controlling latency. And being able to provide flexible client support. Being able to provide protection, either linear protection, ring protection, or mesh protection. I am going to run out of time. So networks, OADMs versus reconfigurable OADMs. The one thing in OTN, everything is an optical add-drop multiplexer. Everything. So it's much simpler than SONET in that regard. Everything's either an OADM or an amplifier. So you only have two types of sites to worry about in your network when you consider it from a deployment perspective, a management perspective. So DWDM is virtually everywhere today and supporting a number of applications, and not just DWDM, but optics as a whole to extend distance. The cloud is very dependent upon optics because of the amount of bandwidth that the cloud is demanding. And actually, the cloud kind of started with remote storage, optical VPNs, being able to separate that network so that your individual customers are sharing the same network, but now those wavelengths are separated, so you have your own wavelength, you have your own wavelength, and they're all traveling across the same fiber, and you still have protection. Your traffic is your traffic, and nobody ever sees anybody else's traffic. Grooming and core router offload as well. You want to do this? Okay. I'm maybe going to make it. So some of the various ways for security techniques that that the industry is starting to support today. So hardware-based security, we do hardware and software-based with a number of algorithms for data path, keying, digital signaturing, encryption hardware that's 142 level 2 and level 3 compliant.
Have you seen people pump up to AES 1024 or 2048 and be able to achieve line rate?
So when you're looking at a network and you're talking about the DoD functionality, compliancy has been type 1 versus type 3. So this would be equivalent to a type 3, and that's the standard. Other than that, we're moving to a type 1. So it's just typically not out there commercially.
Okay. I just didn't know if you had seen anybody working with it, because
No.
I don't like type 3, but if we can get to a type 1 version
So
using,
yeah,
No.
so the argument, and so I worked with some crews out in the Columbia area, and the multi-layering at type 3 effectively gives you the type 1 capability, and in some cases they will give the rubber stamp to say that's fine. And I also work with other divisions that say absolutely not. Due to the sensitivity, it has to be a type 1 standalone hardware.
Or you can just pump type 1 over the medium.
well,
Say again?
generally what
You
you're
could just-
using is you're using type 1 over a type 3. If you're using,
Yeah, I see that all the time.
Yeah.
I mean, this transports type 3, so
Yeah.
that adds additional complexity into your design and architecture.
So folks, I want to interrupt, it's 11 o'clock, so the course time window is
Yeah.
officially over. You guys can stay, continue conversations, but some folks may need to leave.
Yeah.
We also need to scan everybody's badge, so Jim, go ahead and close it out.
Okay.
And,
So I've only got like 4 more here, I think. So Secure Erase, this is a product that we employ that removes all data, non-volatile for validation. So we eliminate all configuration files, executables, libraries, licenses, usernames, passwords, encryption. So pretty much everything gets wiped.
When?
When you employ you employ it when it's typically for anything that you're going to return to us. As well as for disabling physical ports, logical interfaces, disabling the overhead so you can't use the SONET overhead, the data communications channels or GCC to actually log into devices, as well as logical interfaces. And our software, all of our software for our 5,000 series devices, our 6,000, our 3,000 and 5,000 series devices are digitally signed software. We also use imaging hashing with the 6500. And for interfaces, HTTPS, Secure Shell. For SNMP, we support both V2 and V3 for our management interfaces. And for access level most of the industry standards, radius, TACAS, access control list, defining password complexity and aging and password reuse, security profiles. And then ISO 15408 certification. So our 5000 series, 3000 series, 8000 series devices, and 6500, our transport product is on target to be certified next year. Oh. So I was a little over.
No worries. Thank you very much, Jim.
Thank you.
Very informative. If you're an FCM member, as you exit, please get your badge scanned to get credit for the course. If you're a non-member, please put your name and email address on our sign-up sheet, and we'll send you that certificate that you can use to
Oh,
use your
thank you.
credit.
And if,
Thank you folks very
yeah.
much for coming.
And if you guys have questions, I'll be over at the booth for a while today.
We also have a feedback form. If you'd like to give some feedback.
Give me some feedback.
On the course, on the instruction.